most fundamental result in the mass transport theory. So in order to prove that result, to give a complete proof, I need some theory. So I am going we need from measure theory. And then after that, I need some tool in convexa analysis. And I will do that tomorrow and maybe part of next Monday. Okay, so let me start with a brief review on measure theory. So I am going to use the regular notation 2 to the power x. 2 to the power x. This is if x is a non-empty set. This is the set of A in X. So, of course, if X is a set of finite cardinality, then you can 2 to the power S is a set of 2 to the power. If the cardinality of X is n, then the cardinality of 2 to the power x is 2 to the power n. So this is one justification of the notation 2 to the power x. So definition, let X be a non-empty set. A function mu from 2 to the power x onto 0 plus infinity. So the function not only can take a real value, but I am allowed the function to take a value plus infinity, is an outer measure if mu of the empty set is 0, mu of A is smaller than or equal to the sum I from 1 to plus infinity, mu of AI, whenever A is an element of 2 to the power x, AI is also an element of 2 to the power s for I from 1 to infinity, and A is a subset of the union I from 1 to infinity of AI. Okay, so let me make some comment. Often I will say measure, but I mean outer measure. And of course, what I am doing is the difference between a measure and an outer measure. I am writing mu of A for any arbitrary A. If I was using a measure instead, I'll write a mu of A for A in a certain sigma algebra. And I will replace this condition by a different condition. But I don't want to too much comment on the definition of measure, but I am using outer measures. So you can see directly a consequence. Assume mu is an outer measure on X. And let A, B, be two subsets of X. Then the following is true if A. Let me start with something general. So observe that I can write A is A intersection B union A minus B. And these two sets are disjoint. Therefore, if I apply that rule by taking A1 is A intersection B, A2 is A minus B, AI is infinity for I greater than or equal to 3, then it is immediate that mu of A is less than or equal to mu of A minus B plus mu of A intersection B. And later we are going to look the case when do we have equality. So if we are talking about a measure instead of an outer measure, then we'll take A and B to be in a certain sigma algebra. And so this will be an equality. But we'll not be talking about A and B arbitrary. We'll take A and B in a special set. The fact that we have a very general A and very general B, we can only write this inequality. And if A is a subset of B, then mu of A is smaller than or equal to mu of B. So, of course, there, you are going to take A1 equal to B, AI equal to the empty set for I from 1 to infinity. And so you get that remark. So let us look some example because I am going to use this often. Let X be a non-empty set, and so there exists an S naught in X. Define delta X naught to be from 2 to the power X into 0 infinity. So this is defined by delta X of A is 1 if S naught is in A, and 0 if S naught is not in A. So I am writing the Dirac measure at S naught, and clearly it satisfies the first property. Clearly it satisfies the second property because if mu of A equal to 0, there is nothing to prove we are done. If mu of A is not 0, this implies that S naught, if mu of A is not 0, then S naught is in A. Then this implies that S naught is one of the AI, and the right-hand side is greater than or equal to 0. So another example is I am going to define U through several steps. I am going to define the measure of closed interval. Mu of AB is B minus A if A is less than or equal to B. And then mu of A will be the infimum over AI, BI, I from 1 to infinity, the sum I from 1 to infinity, mu of AI, BI, subject to the constraint that A is a subset of the union I from 1 to infinity of AI, BI. So this is the one-dimensional Lebesgue measure. So what I done is when I have a segment, I know how to compute the length of the segment. And then when I have an arbitrary set, I cover the set with countably many segments. And I add up the length of the segment. I get something which will be bigger than or equal to something I'll call the measure of A. And I minimize over all this sum to get the Lebesgue measure of A. So this is the one-dimensional Lebesgue measure. It is easy to check that the first statement holds and the second statement also hold. So I am quickly going to specialize. Most of the time, we will not be working on an arbitrary non-empty set. We'll be working on a topological space. And we will be working with some particular outer measure, which are Borel measures. So let me define what is a Borel measure. But before that, let me comment on one of the homework problems. It is homework problem number 1. Call it exercise 1 of the homework. I think I need something before I can do that. I need to define what a measurable function is. So definition. Let mu be an outer measure. On X. We say that a function f from X, but it can take the value negative infinity, it can take the value plus infinity, is mu measurable. If the following hold. The set where f is less than alpha is mu measurable. For every alpha real number, the set where f equal to infinity is mu measurable. And so I need to say what it means that a set is mu measurable. A subset of X is mu measurable. Call it B. If mu of A equal to mu of A minus B plus mu of A intersection V. So a set B is mu measurable if when you use it to divide any arbitrary set, the subdivision you made is nice in the sense that when you add up the measure of the two parts, you get the original measure. So this is what is mu measurable. It appears only on the right-hand side, and the arbitrary test measure appear on the left-hand side. So once we have that definition, this definition makes sense, and that definition makes sense. So what is hidden behind this is the following. I give you two sets, a set X and a set Y. And I put a Borel sigma algebra on the set X, a Borel sigma algebra on the set Y. I look at a function from the set S to the set Y. So when I take a pre-image in the target sigma algebra, I want to check that the pre-image is in the initial sigma algebra. So what I am saying is the following. So I give myself a set X, and Bx is a sigma algebra on X. And I give myself a set Y, and By is a sigma algebra on Y. Now I consider a function f which goes from X to Y. So this is X, that is Y, and I take a B in a Bx, and I look at the pre-image. Here. So the condition is if B is in Bx, By, then f minus 1 of B is in Bx. Okay. So when that happens, I say that my function is measurable. So I don't have a measure. I introduce two sigma algebra, and I use that to define measurability. Now, I want to compare that to the definition I wrote there. In that definition, I am going to take y equal to r. And I am going to take by to be the smallest algebra containing the open sets. The smallest algebra containing the open set, so the open set in R are the form AB. But the smallest algebra containing this open set is the same as the smallest algebra containing half of the line, right? Because I can obtain this half of the line by a countable union of open set. And if you give me open set, and if you give me half of open interval, and I am allowed to use the complement, I can also write any interval in terms of that. And so the sigma algebra generated by this is the sigma algebra generated by that. So when you look at what I wrote here, this is f minus of negative infinity alpha. So I want f minus negative infinity of alpha to belong to a certain set. And this set is the set of B satisfying that property. So this definition of mu measurability is a particular definition of measurability with respect to two sigma algebra, where the first one is given by the mu measurable set, and the second one is given by the Borel set. Now, what may seem less obvious is I am including this set. I am including the set infinity. So when I am talking about the Borel sigma algebra on the real line, I have to add that set in. So I take all the open sets, and in that I add infinity, and I look at the sigma algebra generated by that set. So this is just to say how this definition is a particular case of a more general definition. So now we can come to the following quick exercise. So I want to make a simple relation between a measurable set and a measurable function. So let A be a subset of X and define the characteristic function of A. So the characteristic function of A will be the function from X to R defined by characteristic function of A at S equal to 1 if S is in A, and 0 if X is not in A. So it is easy to show that A is a mu measurable set if and only if the characteristic function of A is a mu measurable function. Okay. So the set where the characteristic function of A is plus infinity is empty. I only need to deal with that. The set where the characteristic function of A is less than alpha, this is equal to either the whole set if alpha is strictly greater than 1, if alpha is 1, and if alpha is less than 1, this is A. So I think I need to consider alpha. So I need to consider the case where alpha is between 0 and 1. Alpha is bigger than 1. And alpha is less than 0. So this is the set of X in X such that SA of X is less than alpha. So SA of X equal to 0 or SA of S equal to 1.
Less than alpha, then this is equal to A if alpha less than 1?
It will be the empty set.
A complement.
A complement.
Yeah, complement. right?
No.
It's equal to A when alpha is equal to 1, right?
No.
Well, why not? No. It's, when alpha is equal to 1, by definition, key A is equal to alpha, to 1, right?
Yes. So this is strictly less.
I'm sorry.
Strictly less.
Strictly less, yeah.
Yes.
It's still go to the complement, then it's, yes.
Yeah.
So then only the other case is interesting. It's the whole inner space is alpha greater than 1, right?
Yes.
You don't need to,
Yes. And I think it should be the empty set somewhere, right?
The empty set is less than 0, and less than 0 is the set.
Yes. So this should be 0, less than alpha. And if alpha is less than 0, this is the empty set. So this set is mu measurable for every alpha, if and only if each one of these sets is mu measurable for every alpha. But the empty set and S are mu measurable for every alpha, which means that the condition is a complement is mu measurable, and that solves the exercise. So now let me comment on exercise 1.1. This is from the homework number 1. So the goal of that exercise is the following. Okay. I am not going to define what an integral is. I will not take time to do that. But if you integrate a mu measurable function, the characteristic function of a mu measurable set, then you get a mu of A. So there is a relation, this is a direct relation between the measure of the set and the integral of the characteristic function of the set. Now here is the natural question. Assume mu of A is known for all A, mu measurable. Okay. Then, do I know the integral over S of F with respect to mu? So this exercise is saying the answer is yes because of the following fact. Show that if mu is an outer measure, on X, and F from X to 0 plus infinity is mu measurable, then there exists AI is X, I from 1 to infinity, mu measurable, such that F is the sum I from 1 to infinity, 1 over I, the characteristic function of AI. Okay, so this decomposition needs some explanation. So this is a number theory result, right? Okay, so before commenting on the number theory result, I take F non-negative. This is not a big restriction, because if F is arbitrary, I am going to write F as the difference of the positive part and the negative part. So if I can prove this for non-negative function, then I have it for every function. Now, fix a number x. F of x is a real number, and it is equal to this. This number take the value 0 or 1. So this is the binary decomposition, right, which has been used when the computer was born. So I am using the digit 0 or 1 to represent any number. Now one can also wonder what is particular about 1 over, yes?
Don't you mean 2 to the power I, to the I power?
Say it again.
Do you mean 2 with exponent I power y?
To which line?
When you write 1 over y, over I, I'm sorry. Yes.
1 over I.
You talk about binary decomposition.
So I mean 0 and 1. So in my binary decomposition, when I want to represent a number, so I start with maybe 1 plus 1. Okay. The decomposition will be 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, and so on, right? This is the binary decomposition, and this corresponds to 1 plus 0 divided by 2 plus 0 divided by 3 plus 1 divided by 4 plus 0 divided by 5, and so on.
Isn't it 2, 4, 8, 32, 16, 32?
This is not unique, right? This is not unique. What is for yours?
Okay. That's
So,
good.
yes, maybe the terminology binary. This is what I mean by binary decomposition. But maybe my next comment will make a link with what you are saying. So I was about to say there is nothing very particular about 1 over I. Right? One may wonder why I put 1 over I in front of it. All I need, I can replace this by Ri, but all I need is the sum I from 1 to infinity of Ri equal to infinity. That's all I need. And when you are trying to solve, I gave some hints to solve that problem. You can write, there is an explicit way of writing the AI. Yes.
Do you mean also that I goes to 0 when I goes to infinity? But
So-
small numbers.
Yes, so I will go to infinity.
So in this case, yes, but you generalized it considering Ri.
Oh, yes. Okay, here. Yes.
Yes. There.
Yes. You are right. I have to impose that Ri goes to 0 when I goes to infinity. So hence, set C1, set A1 to be the set where F is greater than or equal to 1. And I'm going to define AI inductively. Define inductively AI by AI is the set where 1 over I plus the sum I j from 1 to I minus 1, 1 over j, the characteristic function of a j is less than or equal to f. So you need to check the following point. By induction, check that. So call this fi minus 1. So check that fi is smaller than f for every I. Second, observe that fi is monotone, non-decreasing. And so fi converges if and only if one of its subsequents converges. Now, take x. In x. And we are going to consider two cases. We are going to consider the case where, case 1, x is in AI for infinitely. For finitely. So I want to consider the case that this number is really 0. So the number of I, the set of I in N, such that the character S is in AI, the cardinality is finite. Now I want the set where S is not in AI. The cardinality is finite. And case 2, the cardinality of a set of I in N such that S is not in AI is infinite. So what I am trying to say is the sum I from 1 to infinity of 1 over I is infinity. So I am trying to consider the case where all these terms appear except finitely many of them. If all these terms appear except finitely many of them, then then the limit of fi of S will be plus infinity. And then I would like to consider the second case. So maybe let me rewrite it differently. So case 1, x is not in AI for infinitely many I. Second case, x is not in AI only for finitely many i's. So if you set g of x to be the limit when I goes to infinity of fi of x, which exists because fi is monotone, non-decreasing, then in the first case, you will have that g of s is plus infinity. So since g is less than or equal to f, this will imply that f of s is plus infinity. In the second case, if this holds for infinitely many I, you can take a sequence, aik. This means x is not in aik for some sequence a1, a2, and so on. So when that happens, it means that you need to reverse this inequality. But if you combine that with the fact that fi is always below f, you get that the limit when I goes to plus infinity of fi k minus 1 is f of x. Any question? So now I am going to specialize a little bit more. Now I am going to make statement for particular set S, which are topological spaces. So definition. Let X be a topological space. So a topological space, roughly speaking, is I give myself a set X. I give myself a collection of subset of X. And I call them by definition open set. I have a right to do that if the collection satisfies the following property. When I look at an arbitrary union of open set, I have an open set. When I look at an arbitrary intersection of open set, I get an open set. The empty set is in my collection. The whole set X is in my collection. So by definition, when this property is satisfied, I say that I have a topology. And let mu be an outer measure on X. We say that mu is Borel if every Borel set is mu measurable. We say that mu is Borel regular if mu is Borel and we have an additional property. So among the Borel measure, I would like to select those who satisfy the following property. If I give you an arbitrary set, which is mu measurable, I can approximate it by a Borel set in a specific way. And for every A subset of X mu measurable, there exists B subset of A Borel such that, first of all, A is a subset of B, but if you compute mu of A, it is the same thing as computing mu of B. A Borel regular measure is a random measure if mu of K is finite for all K subset of X compact. So if X was RD, then a random measure is a Borel measure, regular measure, which is finite on set which are bounded, on bounded set. So assume mu is a Borel measure, mu Borel measure, and f from X to R is continuous. So can I say that f is mu measurable? Why? Yes. And the open set are in the Borel sigma algebra and so on. Okay. So this implies F mu measurable. So one can wonder, so I am about to say that when I have a Borel measure, the class of continuous function is a very important class. If I know how to compute with continuous function. If I know how to integrate continuous function, then I will know how to integrate arbitrary function. And if I know how to integrate a characteristic function of set, I know how to integrate a mu measurable function. So we are going to state a series of results which we will prove and show that if you know how to integrate continuous function, this is equivalent to knowing how to integrate a mu measurable function. And it is based on the following first result. Theorem. Let mu be a random measure on RD. So you can see that now I am looking at a very particular set X. We have the following. If A is a subset of RD, then mu of A is the infimum of mu of U, the infimum over U, such that U is in RD is open, A is a subset of U. So I want to draw your attention to the fact that I did not impose that A was mu measurable. I took an arbitrary set A. Now I am approximating A by set U which contain A. And this is the justification of outer. So the property that outer for outside, the property that you can approximate the measure of a set by measure of set which contain that set is correspond to the fact that we have an outer measure. Now I'm going to state a second result, but with a restriction of A. If A is in RD, is mu measurable, then mu of A is the infimum over K, mu of K, such that K in RD is compact, and K is a subset of A. So if I want to approximate my sets by sets which are contained in it and which are compact, so thank you. By sets which are compact, I will be able to do that only if I know that my set A I am starting with is not too bad. It is mu measurable. So I have a set A, mu measurable. There is no distinction between that set and the characteristic function of the set, right? Because if I know the set, I know the characteristic function. And A is mu measurable if and only if this characteristic function is mu measurable. And I would like to say that this is telling me, roughly speaking, there is no big distinction between characteristic function of mu measurable sets and the characteristic function of open set. And there is no distinction between characteristic function of open set and characteristic function of compact set, in the sense that I can approximate one by the other. And eventually, I want to say that there is no distinction between characteristic function of compact set and continuous function. So the result I am going to state and prove, this is what they are saying, more or less. They are saying if I know how to integrate continuous function, then I know how to integrate characteristic function, which means I know exactly what my measure is. So that is an exercise which is based on the following definition. A function phi from Rd to R union plus infinity is lower semi-continuous if the set where phi is less than alpha is closed for all alpha real number. So a direct consequence of that is a lower semi-continuous function is a Borel function, because this is the pre-image of the half a closed segment. So you are asked to solve the following exercise from homework number 1. Phi is lower semi-continuous if and only if. And in fact, I gave an idea of the proof of that. Phi of S infinity is less than or equal to the lim nth phi of xn whenever Sn converges to S infinity. Okay. So I gave enough argument to show this equivalence. And my comment was on the most difficult part. One implication is easier, the other one is more difficult. My comment was on the most difficult part. Now we have the following theorem. So I am pausing to emphasize the theorem because of the following reason. If you are given say, a measurable function, and you are working with a Lebesgue measure, you can approximate that function by a sequence of continuous functions, but it is an approximation which holds almost everywhere. It is not everywhere. So to repeat myself, I am saying, assume X is Rd. I am working on the d-dimensional space. Assume I am working with the Lebesgue measure, and I give myself a function which is mu, which is measurable with respect to Lebesgue measure. Can I find a sequence of continuous function such that the limit is that given measurable function? The answer is yes, but if I am more restrictive, it will be a limit almost everywhere. It will not be a limit everywhere. So this result I am going to state will say that for some particular case, you have a limit everywhere. So let phi from Rd to R plus infinity, be a lower semi-continuous function, bounded below. And you will see in the proof that the fact that it is bounded below can be relaxed. Then there exists function phi epsilon from Rd to R, which are Lipschitz, such that the limit when epsilon goes to 0 of phi epsilon of x is phi of x for all x in Rd. And so this is a strong statement compared to what is done often in measure theory. Any question? So anybody has an idea how to construct such an approximation? So are you familiar with the chain extension theorem, which says that if I am given a Lipschitz function with a Lipschitz constant L, I can extend it and obtain. If I am given a Lipschitz function on a set of small measures with a Lipschitz constant L, I can extend it as a Lipschitz function on the whole space with the same Lipschitz constant. Okay, so what I am going to write will be an extension of the phi epsilon will be an extension of the Mach chain extension function. So proof for epsilon greater than 0, set phi epsilon of x is the infimum y in Rd of x minus y divided by epsilon plus phi of y. Okay, so you can see where I am using data f is bounded below. If f is bounded below, then phi take only finite value. But you can also see that it is enough to assume that phi of y is greater than negative a constant ay plus b, where you allow a to be negative. Because for epsilon small, 1 over epsilon, can write it as 1 over epsilon over 2 plus 1 over epsilon over 2. And 1 over 2 epsilon will dominate A. And this will prevent my infimum to be plus infinity. So what I am trying to say is I will be able to prove the theorem if I replace phi bounded below by this assumption. So is it clear why phi epsilon is below phi? Why? You mean x? call this one, y equal to x in 1, we have phi epsilon of x is less than phi of x. Say it again. Okay. Now I need to check that phi is Lipschitz. So far I have not used the lower semi-continuity property. So let me give a wrong proof of the fact that phi epsilon is Lipschitz, and then we will try to make the proof rigorous. Proof with a gap. And then I will have to fill the gap. Fix y1, y2 in RD. We want to show that phi epsilon of y1 minus phi epsilon of y2 is less than or equal to 1 over epsilon y1 minus y2. So if I show that, then I have proven that phi epsilon is Lipschitz. So in the homework problem, I replace RD by an arbitrary set, and I replace the number by a distance. But you can see that the proof are exactly the same. So here is my mistake. Assume that the infimum is at 10. No, I mean to, okay. Assume that the infimum is at 10. Pedagogically, this is not a good way of doing things because I was putting S on the left-hand side, Y on the right-hand side. They are equivalent. Then phi of Y2 will be less than S2 minus Y2 over epsilon plus phi of S1, phi of S1. Okay? So by definition, phi of Y2 is less than anything with X here. So compute phi epsilon. Compute phi epsilon of Y2 minus phi epsilon of Y1. Then these two things will cancel out, and you will be left with S1 minus Y2 minus S1 minus Y1 over epsilon. And this is clearly less than Y1 minus Y2 over epsilon by the triangle inequality, and we are done. So we can fill this gap if even if there is no existence of a minimizer, because what I am going to do, I am going to write that I can find y1 such that this is greater than that minus delta. And here I will have delta minus delta. minus delta. Since delta is arbitrary, I can let delta go to 0, and I am done. Okay, so in that proof, I have not used that phi is a lower semi-continuous. So my statement is, even if phi is not lower semi-continuous, phi epsilon is a Lipschitz function, and the Lipschitz constant is less than or equal to 1. I am going to write a proof where phi is lower semi-continuous, because I am going to prove that a minimizer exists, and because I need that later. So I claim that given x in RD, there exists y in RD such that phi epsilon of x is x minus y over epsilon plus phi of y. So proof, take a minimizing sequence. Take yn, n from 1 to plus infinity, such that phi epsilon of x is the limit when n tends to plus infinity of x minus yn divided by epsilon plus phi of yn. Okay. So anytime I am minimizing something, I can take a minimizing sequence. Simple characterization of what the infimum is. So phi epsilon by the first part phi epsilon is below phi. So I have this sequence which converges to that. Without loss of generality, I can assume that s minus yn divided by epsilon plus phi of yn is smaller than phi of x plus 1. Okay, so if this limit is that for n large enough, this inequality holds. So if phi of x is finite, we may assume, without loss of generality, that this inequality holds. But this is bigger than y minus yn over epsilon plus the infimum of phi. Because the infimum of phi is finite. So if I rearrange, I can conclude that x minus yn is smaller than 1 plus phi of x minus the infimum of phi multiplied by epsilon. And so Sn is Yn is a bounded sequence. Since it is a bounded sequence, I can extract a subsequence which is convergent. So call data 2. By 2, yn is a bounded sequence. And so it admits a subsequence y and k converges to some y. So how do I finish the proof? I use what?
Now when you use the lower semi-continuity.
Exactly. If I use the lower semi-continuity, this limit f will be bigger than or equal to phi of y. This will converge to x minus y, and I will be done. Hence, phi of x is bigger than. So let me call data 1b by 1b. This is greater than the limit f k go to plus infinity x minus y and k over epsilon plus phi of y and k, and this is bigger than x minus y over epsilon plus phi of y. This proves that this is phi epsilon here. This proves that I have a y for which inequality is satisfied here. So this is greater than phi epsilon of y, right, of x, right? Because phi epsilon of s is the infimum over all the y of this expression. So for this particular y, I have that expression is greater than phi epsilon of y. So this expression is between phi epsilon of y and phi epsilon of y. I can conclude that hence phi epsilon of x is x minus y over epsilon plus phi of y. And the infimum is attained. First summary. I want to write what is there. I want to repeat what I written there. We have proven that given x in Rd, if phi of x is finite, then there exists y in Rd such that phi epsilon of x equal to x minus y over epsilon plus phi of y, and call this 3. So I am repeating that for a simple reason that Once you give me x and you give me y, you give me epsilon, this y will depend on epsilon. So let me add the fact that it depends on epsilon. Observe that by 3, I am going to write the following: x minus y epsilon over epsilon plus phi y epsilon is bigger than s minus y epsilon over epsilon plus the infimum of phi. But this is phi epsilon of x, but phi epsilon is less than or equal to phi of x. So let me rewrite what is there. It is x minus y epsilon is smaller than phi of x minus nth of phi multiplied by epsilon. And this shows that the limit when epsilon goes to 0 of y epsilon must be x. So if I plug that fact here, call that 4. By 4, the limit when epsilon goes to 0 of y epsilon is x. Now, I want to plug that here and use it. So I let epsilon go to 0. This will be bigger than or equal to phi of x, because y epsilon goes to x. And that, how do I get rid of that? So I want, this is our ultimate result. The limit of phi epsilon is phi. We have proven that phi epsilon is less than phi. Therefore, the lim sup of phi epsilon is less than phi. If we can show that phi is less than the lim f, we are done. I have this information. I have that information. If I use lower semi-continuity, I know what I can say about this limit. But that term, what do I do with it?
You have that x minus y epsilon over epsilon is bounded.
Yes. Yes, it is bounded, but it may go to a positive number. I want, so it may go to a positive number.
Branch bound from below, right?
Exactly.
We can do it 0.
Exactly. This is a non-negative, a positive number. The limit will be non-negative, and so I don't care what it is. By 3, phi epsilon of x is greater than or equal to phi of y epsilon, because I can throw away the non-negative term. Now I can add the lim f. when epsilon goes to 0 will be bigger than the lim nth when epsilon goes to 0. But lower semi-continuity will tell me that this is bigger than phi of x. And so I am done. Call this inequality 0. And call that inequality 5. By 5, by 0 and 5, the limit when epsilon goes to 0 of phi epsilon of x is phi of x whenever phi of x is finite. So now I can come back here, although it is not needed. I can come back here and say, now I know that this converges to phi of x. This must then converge to 0, otherwise I will get a contradiction. So I can draw a stronger conclusion than that. Here I say y epsilon converges to x. I can write a rate of convergence. I know that now x minus y epsilon divided by epsilon will converge, must converge to 0. Otherwise, it will contradict this equality. So I don't want to complicate things. You see that I have excluded the case, I mean plus infinity. So lower semi-continuous function, you should never achieve a value negative infinity. Never. So what I meant was plus infinity. And I don't want to cover the case plus infinity, so I'm going to remove this. This is the theorem I have proven. So what does this has to do with a characteristic function of compact set? Okay. So let me ask you to take a guess. I look at the characteristic function of an open set, the characteristic function of a compact set. Which one of both will be lower semi-continuous? One of them is lower semi-continuous. One of them is upper semi-continuous. Which one will be lower semi-continuous? Exactly. So let us check that. Remark. If O RD is open, the characteristic function of O is lower semi-continuous. So proof. Suppose Sn in RD converges to x infinity. If x infinity is not in O, then the characteristic function of O at S infinity is 0. If S infinity is not in O, the characteristic function applied there is 0. That is less than the limit f, the characteristic function at Sn. Because the characteristic function applied to Sn is greater than or equal to 0. If x not is in O, that it means that for n large, Sn is in O. Then there exists, because O is open, there exists S not such that Sn is in O for n greater than n naught. Hence, the lim f over n, the characteristic function O as Sn is 1, which is the characteristic function of O at S infinity. So according to the theorem I just proved, it means that the characteristic function of any open set, you can write it as a limit of a Lipschitz function. Therefore, if you take the characteristic function of a closed set, if I take a closed set F, the characteristic function of F is 1 minus the characteristic function of the complement of F. And so the characteristic function of F is upper semi-continuous. So let me repeat another remark. If F is in Rd, the characteristic function of F is 1 minus the characteristic function of F complement. Hence, if F is closed, by the previous remark, the characteristic function of F is lower semi-continuous. Negative, the characteristic function of F is lower semi-continuous, which means the characteristic function of F is upper semi-continuous. So all I am interested in is I can approximate the characteristic function of O of F complement by a sequence of continuous functions. It is immediate that I can approximate the characteristic function of F by a sequence of continuous functions. Any question? So I am trying to see if I can change a little bit the topic. If I can change the order so that maybe you are not hearing too much the same thing. So I am not going to state a losing theorem. So this theorem says if I have a special measurable function, meaning a characteristic function on an open set or a closed set, I can write it as a pointwise limit of continuous function. Losing theorem will tell you that it will not be a pointwise limit, but it will be up to a set of zero measures. So losing theorem is stronger than this theorem because in the case of losing theorem, you take an arbitrary measurable function. But it is weaker in the sense that the limit you get in the case of losing theorem is a limit almost everywhere, not a limit everywhere. So theorem. Losings. Let mu be a Borel. Regular measure. On RD and so I am not assuming that this is Borel. I am assuming that this is Borel measural, regular, and let f from RD to R be a mu measurable function. So the theorem I am going to state will say I can approximate. I want to say I can approximate f by continuous function. But what I am going to state will be I can approximate the restriction of f to set of finite measure by continuous function. But this is not very far from the goal, because if you can do it for a set of finite measure, you write your set of finite measure as a countable union of, if you can do it for a set of finite measure and you are given an arbitrary set, you write the arbitrary set as a countable union of set of finite measure, and you add that to the result. Let A RD be a Borel function, be a Borel set, such that mu of A is finite. So I can replace a Borel. The fact that I impose it as a Borel set instead of just a mu measurable set, this is not a big restriction, because we see that if I can prove it for a Borel set, if you give me any set which is not Borel, I can put it inside a Borel set of same measure, and I will apply the result. So let me repeat again. Here I am imposing that A is a Borel set, but this is equivalent to imposing that A is mu measurable. If I replace that by A mu measurable, both theorems are equivalent. For every epsilon greater than 0, there exists A epsilon, subset of A, mu measurable, and F, a continuous function, such that the set where F epsilon is not F, intersection the set A, if you compute this measure, it is less than epsilon. So in fact, when you look at losing theorem in the literature, it is stated into two result. When you combine those two results, you get this one. So the way Lusin's theorem will be stated in the literature, they will say there exists a compact set K epsilon such that you draw this conclusion. And they are going to take f, a continuous function, on that compact set. And then in the second step, you can show that every continuous function on a compact set can be extended to a continuous function on the whole RD. So if you combine both results, this, you get this result. So this one contains more than what is referred in the literature to Lusin's theorem. So it may be better that I finish today with the measure theory stuff. So these are classical results. This is why I am not proving everything. This is not the purpose of this course is not measure theory. And so it may be a little bit more difficult to digest.
In your statement, you put then F for every epsilon with dz, there exists a epsilon containing a mu measurable and
F epsilon. F epsilon continuous.
Why is it clear with the a epsilon?
So this will not make much sense if I don't add data a minus a epsilon is smaller than epsilon. So the measure of a epsilon is almost the measure of epsilon, and the set where f epsilon and f are not the same is a set of small measure.
And it should be compact to the a epsilon. You cannot guarantee that, right?
You can take it to be compact. Because, so here is how you see the equivalence. If it is not compact, I approximate it by a compact set. So it is going to change epsilon to 2 epsilon.
No, because there is nothing in this statement about compactness of a epsilon, but of course you choose a epsilon compact, right?
Yes, if it is not. So assume I prove it for a epsilon, which is mu measurable. I stated that result saying you can approximate from inside every measurable set by a compact set. Then it is true for that small set. I know. Okay, I will finish now.
Can I ask a question?
Yeah.
You were talking about the purpose of the course, that it was not exactly measure theory.
It is not that, it is not exactly. It is not measure theory.
So you were in the middle of it, and I would like if you could use these last 10 minutes. I would like to hear a little bit.
Okay, so let me make the description of the course. So let me start with something a very simple case. I give myself two particular measures. I am using measure again. And I define the distance between S0 and S1 to be the norm of S0 minus S1. Okay? So, given two Dirac masses, I define the distance between them that way. A little bit more complicated case. I give myself the average of two Dirac masses. Okay. And I want to define the distance between these two Dirac masses. I want a definition which will coincide with this definition. So you see that if I change the order of the SI, so I have S1, S2, S3, Sn. If I reverse the order, I have the same measure here. So I better have a definition which is invariant under permutation. So I am going to write the sum, the distance between Si minus Y sigma I. So let me put a square here. Square. And I am going to minimize over sigma permutation of n letters. Okay.
You also need to normalize by n, right?
Thank you. 1 over n. Yes, it is important to normalize by n because I am going to let n go to infinity, and so I'll have a problem. So I have defined the distance between two Dirac masses. There are two average of Dirac masses. This is still particular. I want the distance between two arbitrary measures. W2, general case. W2 between mu naught and mu 1. I am going to approximate a mu naught average of Dirac masses. And mu 1 is also the limit of average of Dirac masses. But there is a problem in this definition. I have written a definition which depends on the sequence of approximation. So I need to do some work to prove that the limit is independent of the sequence. So if you try to fill this step, this is one way of constructing the theory. But I am going to choose a different way, which is what is the most used, and that is one of the fundamental results in the theory. It is called a duality result. So let me state the duality result. Okay. So what I am saying is technically, if I am going to try to fill this program, it will take some effort. So instead of that, I am going to say, let me try something different. And here is the thing different. Another approach. I want to work directly here. And so I will need to know what will correspond to permutation. So given mu naught mu1 probability measure. I am first going to look at the analog of this. I would consider gamma, which have mu naught and mu1 as marginals. So I am going to rigorously define that, but let me use your intuition in the following. Gamma will be a measure on RD cross RD, and the first projection of gamma will be mu naught. I want to define what it means. The second projection will be mu1. So that corresponds to what are here. Here, my gamma will be 1 over n, the sum of delta Si y sigma I. So for each permutation, I will have a gamma. Now, this integral will correspond to the integral of x minus y squared gamma dx dy. So if you plug that gamma there, you will see that you get exactly this expression. And I'm going to minimize over gamma. So one of the fundamental theorems of the theory says that, so when I compute this directly, this is a minimization problem which is not very pleasant if you try to write the Euler-Lagrange equation. So you establish the following fact. You introduce Lagrange multiplier, u and v, which are functions. Subject to the constraint that u of x plus v of y is less than x minus y squared for every x and every y. So this is like a magic problem I introduced. But the idea behind that is the Lagrange multiplier. So once you establish this duality result, it helps doing many things. So once I do that, let me tell you in 2 minutes the power of that theory. Some of you are familiar with the log-Sobolev inequality, any of you, or the Brown-Minkowski inequality. Okay. So the Brown-Minkowski inequality says that if I take a K1, K2 in RD compact, convex, and I look at the volume of K1 plus K2 to the power 1 over D. I compare that to the volume of K1 to the power D, 1 over D, plus the volume of K2 to the power 1 over D. The Brown-Minkowski inequality tells you that you have this. Okay, so there this is an old result which it takes some energy to prove it. Now, choose the function f of rho. Rho is an arbitrary function to be the integral of rho to the power r ds. So this is a function, f is a function which I define on the set of probability measures which are absolutely continuous. You have a metric. The W I wrote earlier, one can show that is a metric on the set of probability measure. One can describe the geodesic of that metric. If you prove that this function, capital F, is convex along geodesic, you see that Brown-Minkowski function is a direct, Brown-Minkowski inequality is a direct consequence of that. So you are also familiar with Poincaré inequality, for instance. You have a question? You are also familiar with Poincaré inequality. You choose an appropriate function f. Sorry. For Poincaré inequality, depending on the Poincaré inequality, I am going to choose a of rho ds. So a of t was t to the power r here. So I'm going to choose an appropriate function a. And you can show that if capital F is convex along geodesic, then this gives you the log Sobolev inequality. Immediately, it is a 3-line proof. But I am also going to spend 1 week showing how this distance has been one of the challenging problems in kinetic theory is the kinetic Vlasov equation. There are many questions which cannot be answered. So one can use this metric to give some modest answer on that equation, which remains still a challenge in general. So I am planning to spend maybe a little bit more than 1 week talking about the kinetic Vlasov and just give a brief description why convexity along geodesic will imply Brand-Minkowski inequality, which is a geometrical. So these are very unexpected facts. You are interested in something from the PD point of view, and then it turned out that geometers, people doing optimal design, realize that it is applicable for solving the problem. This is not a mystery, because one can rewrite the W I wrote, one can rewrite it as a kinetic equation. One can write it as energy, kinetic energy. And so when you think about it, it is not a mystery that it has a connection to that many field. So I will stop here.